y equals kx, y equals k over x. If one increases, so does the other. If one increases, the other decreases. Yes, there are lots of because I forgot to turn on the video. Okay, so we're going to compare y equals kx, which is direct. And then y equals k over x, that is my inverse. Inverse. We're going to solve for k. Now we've done this before for direct variation. Some of you even remember this, right? How do you solve it for k? You divide by x. So k equals y over x. So in a direct variation, y equals kx, k equals y over x. Divide to find the constant variation will be the same. Every y divided by every x, you're going to get the same k. Let's solve this side for k. Well, how do you get k by itself here? Multiply by x. Remember the trick that's in the denominator? You just multiply to get rid of it. Do it to one side, do it to the other. Multiplication property of equality. So xy equals k, or we can use that symmetric property of equality to turn around. Look at the difference. Okay? Now for some people, they get very confused with this. Well, this is dividing and that's multiplying. Yeah? Like you're solving. Yeah. Yeah. So because I'm multiplying here, solving for that is a divide. And because I'm dividing here, solving is a multiply. Alright, so remember that. Telling the difference. Now we did this on our warm-up. How did you figure out if something was a direct variation? We solved for y, right? And when you solve for y, you said, gee, did it match this model of y equals a number times x? Well, we're going to do the same thing. Let's solve for y, but we're now going to compare it to two things. If it's not this one, maybe it's this one. Or maybe it's neither of them. So, y. I want y by itself, so what needs to happen? Divide by x, y equals negative 4 over x. So is this a direct variation? Does it look like y equals k times x? Yes? No. Does it look like y equals k over x? Yes. Right? It's a constant divided by x. What's my k? Negative 4. This is an inverse variation because it looks like y equals k over x. Alright, let's solve this guy for y. What do I need to do here? 2, both sides. So y equals 2x. What does this one look like? Direct. Y equals kx. This is a direct variation. What is the k? 2. Alrighty, this one. Direct inverse. It's already solved for y, so I don't have to kind of do anything other than kind of look. Does it look like a direct variation? Does it look like an inverse variation? Which one? It doesn't look like either of them. It looks a little bit like a direct, except for this plus 3. What's the problem with that? Well, the slope's fine. That's fine. That could be, But what's the deal? Right, this one is always a y-intercept of 0. It's not a 0, so it's not a direct variation, and it's certainly not a k over x. So neither. So you could be one, you could be this one, this would not be over those. Yeah, okay, so again, let's compare. Direct variation, y equals kx, k equals y over x. And you don't have to necessarily memorize that. You can always rederive your k. Right, divide by x, divide by x. With inverse, you're starting with a division, y equals k over x. So when you solve for k, you get a multiplication. The big idea here between the difference is if one variable increases, so do the other, or if one decreases, so do the other. They change kind of in the same way. Whereas for inverse, if one gets bigger, the other gets smaller. The graph of this, now look at it, it's a line that goes through, looks like this. It goes through the origin. Always. How come it always goes through the origin? The y-intercept is 0. So I'm always going to go through the origin. Now, the graph of an inverse variation, that's a hyperbola. What? It's a hyperbola. Excuse me. No. No, that wasn't. No, a hyperbola. Let me show you what that is. The hyperbola. Look at it. I'm going to graph y equals 1 over x. You can too if you want to. do you tell them it's a polynomial? Has to have a whole number exponent. What's this one's exponent? X is -1, right? Is this a polynomial? No, it's not a polynomial. You can't have an x in a denominator because it gives you a negative exponent. So it's not a polynomial. So polynomials don't look like this. But it's another creature. It's this guy. A little hard to see it. I have another picture of it over here. Wow. That's the branches of a hyperbola. Now, I don't know if you recall, we talked a little bit about the conic section. So remember how our parabola is a slice kind of through here? The hyperbola is when you kind of slice through both cones. So that's why there's two pieces. Because we're kind of slicing through both cones here. Getting two pieces. Kind of weird. Now, it has what we call asymptote. This is a lovely little math word. And what it means is when you're looking at these little green curves, think of the axes as being brick walls. They cannot cross them. They can't get across them at all. And not only that, they will never even touch it. It's like they're radioactive. You can't touch that wall. So it will never, ever get there. Never, never, never. Okay? So, kind of strange concept. I mean, you can keep going. It's like you're going to get really close to it. So how come we just don't ever get there? And how is that even possible? I mean, that blew my mind when I first learned about asymptotes. I'm like, how could it never get there? It doesn't. It's like, somebody here must know about Zeno's paradox. Anybody? You know that? Okay, what that is like, let's say I'm going from here to the wall, and I go halfway there. Okay, I'm close to the wall, right? I'm not there yet. And then I'm going to go halfway from my distance down. Not there yet. I'm going to go halfway. And I'm going to keep going halfway, halfway, halfway. Do I ever get to the wall? No. I'm going to get pretty darn close, but I'm never going to get there. Why not? Half distances. There's always going to be a little bit left over. It's kind of a freaky thing. So that's kind of what an asymptote is. So if you think of these axes as brick walls, they can't get past it. And they're a bit radioactive. So they're going to get really close to it, but they will never, ever, ever, ever get there. So that's what an asymptote is. We'll learn a lot more about those guys. I want to say algebra 2, yeah. All right. Let's graph this guy. Y equals 10 over x. Just kind of spread those branches a little bit. 10 over x. Okay. So remember our quadrants? Remember how quadrants work? We got 1, 2, 3, and 4. So where are we seeing the branches? Which quadrant? 1 and 3. Now I'm going to make the I was going to say this function. Is it a function? Wait. Is it a function? No. No? Yes. Yeah. Well, which is it? No or yes? Yes. Why? Because they don't intersect going through x-axis. Right. If this was to cross and this was to cross, then we would say no. Right? Right. If this guy crossed over and that guy crossed over, then I can find an x with more than one y. But each x has one and only one y value. We can do the vertical line test. You can see that. So it is a function. Now, if I make the function negative, watch what happens if I can figure out how to get there. I'm changing. It's negative 10x. So what happens to it? Maybe you can compare it to this one. Here's a positive number for k. Here's a negative number for k. What happened? It swapped the quadrants. Now I'm in quadrants 2 and 4. So a positive k will be in quadrants 1 and 3, and a negative k will be in quadrants 2 and 4. So just so that we know what we're looking at, what kind of variation we have. Okay, so here's y equals 3 over x. Looking at it. Here it is. It's a hyperbola. It will never pass through the origin, unlike a direct, which is always through the origin. So that's really different. Never will be here. It also will never cross the x or y axes. They are asymptotes. It will never get past them. They're brick walls. And if k is negative, we're going to swap the quadrants. So from 1, 3, 2, 4. Yes? So this one should stay in one quadrant? Yeah. They're kind of tracking here. This will go up forever and ever and ever. This will go out forever and ever, but it never quite gets to the mark. Yeah. Yeah, you can do funny things with this value, and they can come in here and they can change. But the general channel shape kind of always looks like this. Channel shape. Okay, so let's compare what we got. So here's a direct variation, here's an inverse variation, right? They're very different, right? This is a line that goes through the origin, and our constant of variation is the slope. This is a hyperbola that never goes through the origin, is asymptotic to the axes. Those are my asymptotes, the brick walls. A positive one, positive constant of variation, you'll see the branches in 1 and 3. If you have a negative, you'll see it in 2 and 4. And that's probably all we need to know about them for now. You get to, I'll pursue you learn more. Yes? Okay, can I finish this first and then we'll talk about it? Okay, now, looking at these guys, can I figure out if I'm looking at a direct, an inverse, or neither? So I'm looking at this guy here. What's this? Why? It's a line that goes through the origin. What about this? Inverse. It's a hyperbola. Is it going to have a positive or negative K? Positive K because we're doing these quadrants. How about this guy? Neither. Well, it looks like a hyperbola, so why isn't this inverse? I'm not allowed to cross the axis. Is this even a function? No. My inverse ones will be function. So nope, not good. And this one. Why isn't it direct? It doesn't go through the origin. Alright. Yeah, so we can just look at them, we know what we're seeing. Alright. Now, we did this in our warm-up, I'm on the back here. We did this on our warm-up for direct variation, right? How can we tell if we're given a table of values, how do I know if it's a direct variation? I made a new column, right? For direct variation, you say K equals Y over X. And then we did Y over X, Y over X, Y over X, right? And if we got the same number, we got a direct variation. So let's answer that question first. Is this a direct variation? Well, what's that over there? Who's got their calculator? What's 2.4 divided by negative 5? Negative 0.48. Alright. What's 4 divided by negative 3? Negative 1. Okay, look at the table. What's 4 divided by negative 3? 1. Okay. Well, look at this. They're different already. It's direct. I know it's not a direct variation. Now, how do I check for inverse? What was K? XY, right? Because if Y equals K over X, to solve that for K, we multiply both sides by that X. So let's see if I get, what is negative 5 times 2.4? What is negative 3 times 4? 4 times negative 3. 8 times negative 1.5. Is it? You do it? 24 times negative 0.5. That one I think it will be easier to see. So what can we conclude? This is an inverse variation. Inverse variation. What is K? And what is the equation of this inverse variation? Y equals negative 12 over X. You start with your model, you found K, plug her in. Y equals negative 12 for this K. So it's the same kind of idea, it's just we're using a different function for it. So in summary, if you're given a table of values to determine if data is a direct variation, inverse variation, or neither, first test to see if it's direct. Divide Y by X. Get the same number? Direct. Try inverse. If that doesn't work, multiply the X and the Y. See if that works. If it doesn't, then it's not inverse yet. So if I'm looking at this guy here, direct, inverse, or neither, let's try direct first. So let's do Y over X. 15 over 3. Where'd you guys go? Okay. 25 over 5. And 17.5 over 3.5. Okay. So what is this? Direct. What's the equation? Okay. When you come back for lunch, figure out what this is. Neither. So we have another example. Let's remind ourselves after that break. First, you decide if it's direct. You look for K, which for direct would be Y over X. What's 1.4 divided by negative 10? Negative divided by 2. Okay, what? Because I need to even bother with this one. This is a direct variation. I'm not getting the same k. Let's see about inverse. So inverse is xy, right? K is xy. We multiply them. So what's that? Negative 14, right? What's that? Negative 14. Negative 14. So what can I conclude? It's an inverse variation. What would the equation be for this inverse variation? Y equals negative 14 over x. Excellent. Let's try this guy. Let's see if it's direct. Direct is you look at y over x. 5 over 10 is 1/2. 8 over 16, 1/2, looking promising. 2 over 8, oh, that's 1/4. So is it a direct variation? Nope. Let's see if it's inverse. X times y. That's 50. 16 times 8, what's that? 128? I don't even care what that one is, right? It's kind of. So it doesn't have to be one or the other. It's under that one. So there we go. That's how we do those. What else we got? Let's see. The variables x and y vary inversely, and y equals 6 when x equals negative 3. Very inversely. So now, because we have two different possibilities, I'd like to circle, make a box around something to remind myself that's what it is. You might even want to put the model in front of you so you don't confuse the two. And then k equals xy, right? Multiply both sides by x. Let's see what they want to know. Write an inverse variation equation that relates x and y. So I'm looking for the equation. How would I do that? Well, first of all, what's the model? So I basically have to find this k, and I've got my equation. How do I find k? Well, what is it? You're on the right track there, Alex. K equals what? Yeah, k equals xy, right? So it's going to equal whatever my x value is times its corresponding y value, which is negative 18. So Alex, what's the equation?
Y equals negative 18.
Great. Y equals negative 18 over x. Just find the k, put it back in, substitute it in the actual equation. Remember, don't do the silly stuff that happened with direct variation, where we didn't understand what I meant by what's an equation. I want the y, I want the x. You find the value for k. Find the value of y when x equals 4. Now, I've got the equation. Right? So now you're telling me that x equals 4. So substitute in. Well, let's see. I can reduce that fraction, negative 9 over 2. So the value of y is negative 9 over 2 when x equals 4. Just plug it in. And again, we've done all these same things when we were working with direct variation, but now we're just using a different model for it. That's the same general idea. Any questions on this so far? Yeah? All right. Let's look at a word problem because, that's life. Life's like a word problem. So let's see what we got here. A theater company. A theater company plans to hire people to build a stage set. The work time T in hours per person varies inversely with the number T of people hired. Now I have to say, when I do these, I spot right in on some of these words. I look for that. Is it inverse? Is it direct? Is it telling me? Inverse. So then I write out, what do I know about inverse? Y equals kx and k equals xy. Just to kind of have it there for my reference if I need it. Now what is varying inversely? The work time, T, varies inversely. Now remember when we did the direct, we said varies directly means equals k. Right? You see those words, you put in equals k. Well, what am I going to put in there for inverse? Equals k over what? The number of people. I'm saying use a T for that. Okay, so now here's my model. I basically want to find a k. Now they're going to give me an example, just like with direct variation, they're going to give me a T and a P that go together. So then is everybody listening? Because I see a lot of people not listening. Okay? Eyes on the board, please. Alrighty. I'm going to rewrite this as k equals pt. How come I can do that? I multiply both sides by p. And so I got k equals, well, what do I know? If you have 25 people, it takes how long? 300 hours, right? There's the point that they're dealing with. Now what is 25 times 300?
7,000.
Right? So that's my k. So what do I do with that? Put it back in my model. T equals 7,000 So in this situation, time varies inversely with people. 7,500 is your constant of variation. Now they're going to ask you to either find T or to find P. So find the work time per person if the company hires 30 people. So are they giving me, right, they're increasing the number of people? What do I expect to see here? A number bigger or smaller than 300 if I increase the number of people? Smaller, it's inverse. If one goes up, the other's going to go down. So where does the 30 go? Is that the T or the P? So we do that. Over 30, well what's that? 250 hours. So does that make sense? I added more people, it's taking less time. So if you go through this and you get a number bigger than 300 and you, wow, I must have made a mistake somewhere, that doesn't even make sense. If your number of people goes up, the student went up, then your hours should go down. Now let's say it said, find how many people you need for it to take 200 hours, something like that. What if they said that? We only have 200 hours, so how many more people do I need to get? So here's the equation I have. Right? So now where does the 200 go? It goes to the time. And now I get kind of a funny looking equation. It's not hard to do, but it might make you pause for a moment. How do I solve that for P? Do I have to do what? So P equals 200 over 7,500? Well, you're on the right track. You really is on the right track. I'm going to go back to this. So I'm going to solve this now. I'm going to multiply both sides by P. So 7,500 equals P times T. Now I already know what T equals. Why don't I solve this for P? So I'm going to divide by T. Oops. So P equals 7,500 over T, right? If I solve for P, I'm going to divide by T. So what are the two equations that I have? T equals 7,500 over P. T equals 7,500 over T. So which? You can basically put these in either place. Doesn't matter where these go. Not really. So you're basically always going to be dividing this K by whatever number it is with you. So I'm going to use this equation because now I'm finding people. So people equals 7,500 over 200. What do we get? What's 7,500 divided by 200? 37.5. How much? 37.5. You got to get that half person. So what would we probably say here? 38 people, right? So if you want to get this done in a certain time, 38 people. So either way, this is way easier than direct variation. Direct variation, you have to be so careful that you kept track of who went where. With these, you're pretty much taking your constant variation and dividing by the other number, and you get the answer you want. I think it's easier. So let's do one more example here. Anybody in the orchestra? Yeah? Violin? No? Violin? No, what do you play? Viola. Oh, you play viola. It's like a big violin. Yeah. So, it's definitely viola. The length of a violin string varies inversely as the frequency of vibration. So right away, because you're going to get like a bunch of word problems. Some will say varies directly. Some will say varies inversely. So you want to hone in on what's going on here. And I like putting my little models up right so I know, okay, this is what it is. It's going to be different if it was a direct variation. I got this here. What does? The length of a violin string varies directly as the frequency of its vibration. So length varies directly is the equal K over frequency, right? That's a direct variation. They're going to give me values, aren't they? They always do. Yes, ma'am. This is called an L. Cursive. Cursive. They don't teach cursive anymore, do they? I use it because otherwise it looks like a 1. So I use second grade. I thought they didn't teach cursive anymore. Me too. All right. So anyways, what do I know? The 14-inch, a string that's 14 inches long vibrates at a frequency of 450. So let me put this back K equals. I think that's a little easier. It's length times frequency. So the length is 14, 450. Well, what is 14 times 450? Oh, okay. So length equals 6,300 over F, right? Right? I just plug in my K value. I've got an equation. Now I can automatically get another equation. What's an equivalent equation? I can write it there. Equals 6,300 over L. So I really have two. So I don't care what they give me next. They're going to either give me a frequency or a length. I'm ready. So find the frequency of a 12-inch violin string. So which one of these do I want to use? The second one, right? I'm finding frequency. They're giving me length. So the frequency is going to be 6,300 divided by 12, which is 525. What's the units? Cycles per second. Of frequency rolls. There we go. Easy or hard? It really is. If you got direct variation, it's very, very similar. Just make sure you're setting it up using the correct model. All right. One last thing to talk about, and I want to make sure. Oh, we'll go back before. We're writing down. Yeah. What I want to do while others still writing is, sometimes, as in real life, it's very rare in real life where you can say, this thing varies directly with that, so let's do this. Then you say, here's the behavior. Something has this value and something has another value. When you're doing a certain situation, you have to figure out whether it's inverse or direct variation based on the situation. So I've got some situations that we're going to look at, and you're going to decide, is it direct or is it inverse? So let's look at the first one. The number of hours you babysit and the amount of money you earn, are these things related directly or inversely? What do you say? Directly, how come? Exactly. As the more hours you work, the more money you're going to make. The less hours you work, the less money you make. How about this one? The number of hours it takes to do a science project and the number of people working together on the project. I'm going to give it just a little bit of insight. Some of you are seeing it right away. I want to give everybody a chance. When you think you know, raise your hand. You think you know, raise your hand. Emma, what do you think? Inverse, how come? Okay, so we have more people. Theoretically, right? It's going to take less time. Why do I say theoretically? Do you ever have a group and they give you lots of people and then it's just like, now you gotta handle people problems. So, yes, mathematically, yes. In real life, the number of minutes spent running and the total distance that you've run. Alex, what do you think? Direct. Because? The number of people at a party and the amount of pizza that each person will get to eat if there are 10 people in order. So think about that. What do you think? What do you think, Andrew? Inverse, how come? Yeah, so when it comes to food, this guy's right on. It's like, yeah, figure that one out. That's important, right? So, yeah, so let's say there's 10 people and you got 10 pizzas. How many pizzas do you get? Yeah, whole pizza. What if 20 people show up? Increase the number of people. Half a pizza, the amount you get goes down. So that's you have to do it. What? You would? Yeah. How about the whole pizza? Yeah, probably. See? The thought of that just makes me like, but you can do it. So anyway, in a nutshell, inverse direct variation. Are there questions? All right, great.